Greetings, everyone. Welcome to the 77th semi-annual Kieval lecture. Something around 38 and a half years. I'm Jeff Haig. I chair the mathematics department and the computer science department. This evening's talk is mathematical, and I will soon introduce the person who will introduce our invited speaker tonight. But first, I do want to say a few things about Harry Kieval, who was a professor here until 1979. I'm going to read from some text that I have. So bear with me here. Professor Emeritus Harry Kieval was a generous man who deeply believed in undergraduate education, often crediting his academic opportunities to the numerous scholarships he received as a student. Dr. Kieval established the Harry S. Kieval Scholarship in Mathematics at Humboldt State in 1979, the year after he retired. As much as $3,000 in scholarships is presented annually to outstanding math students. The students are chosen by the mathematics faculty based on their scholarship application, academic performance, and faculty recommendations. Now, I know this year's Kieval scholarship for the coming year, that is, we haven't made our decisions yet for this year. Applications are still coming in. However, I know I had dinner and saw our current Kieval scholars, and I am not seeing them. Drake Woolsey and Swan Park were here at the 4 o'clock talk and assured me that they would be here. Maybe they thought it was 7:30. I don't see Drake or Swan.
They were talking with Ken Owens.
Yeah,
They were talking with Ken Owens.
just at 7 o'clock? Or?
Just as I walked out of the building.
Okay, so they are the current reigning Kieval scholars. Next year's scholars to be determined. A little more about Harry. The Harry S. Kieval Lectures in Mathematics, which Dr. Kieval also began in 1979, bring renowned visiting experts in the field of mathematics to campus each semester. The lectures are offered to students and the public. A little more. A native of Brooklyn, Harry was a longtime benefactor of higher education, supporting not only Humboldt State, but Southern Oregon State University in Ashland, where he resided during his retirement, Cornell University, where he received his bachelor's degrees in both physics and mathematics, and the University of Cincinnati, where he earned his PhD in 1943. His generosity continued well beyond his lifetime, as we are bearing witness to today. His gift through his estate, combined with the funds from his charitable trust, assisted in providing endowment to support the Kieval Scholarship and Lecture Series. In addition, the gift from his estate, and this is written in the future tense because it was written in 1997, but I'll read it as if it's in the past, made possible the remodeling of Siemens Hall 128. So yes, back in 1997-98, they remodeled SH 128, and it is the Harry Kieval classroom. Several of us in the room were here, and we're so excited, and we still are, although we don't get down there as much. It's you just don't get down there. Is the floor plan still the Fibonacci spiral? Have you been? Your office is in Siemens.
It is, and now I understand the story. So thank you. So like something new.
Okay. Harry also donated the sundial. I tried to find an image of Harry. They're out there. I didn't come across one.
Oops.
Oh,
It's going to sleep. Yeah, let's see if I can.
oh.
Don't worry.
Okay, well,
I'll look it up.
if you go outside of Siemens Hall and the library, you will see the sundial that Harry donated. And I have checked it for accuracy, and my colleague Yanasco reminds me that it is
Yes.
exactly right. Or exactly 1 hour off. Okay, so maybe not in the future. In the near future, we may have it's either always one hour. Ken will recalibrate. I know he's doing it. Finally, let me introduce Jen Katz, Provost and Vice President of Academic Affairs. Jen came to Humboldt 2 years ago from the Metropolitan State University of Denver. Think about that. 2 years ago, Jen accepted a position, the most demanding position on any university campus, at a university undergoing institution-level transformation to a polytechnic institute. Oh yeah, during a pandemic. Jen is necessarily one of the busiest people on campus, yet finds time to add a personal touch to much of her work, and we are glad to have her here tonight to introduce our speakers. So I give you Dr. Jen Katz.
That was really kind. I was so excited to be here. I was saying earlier, tonight's the first night that I've been able to participate and do introductions for lectures, and I get to do 2 introductions back to back in the same room for the first time, right? So, wild. Okay, so I'm really excited to be able to introduce Dr. Jesus de Loera, close, from UC Davis. He was born and raised in Mexico City and completed his BS in mathematics at the National University of Mexico in 1989. He completed his PhD in applied mathematics at Cornell University and has been a member of the faculty at UC Davis since 1999. His research is in the areas of combinatorial and computational applied mathematics. I can barely say it, much less probably do it, so it's pretty freaking impressive. He is an expert in the field of discrete mathematics. His research has been recognized in several ways. He was awarded an Alexander von Humboldt Fellowship in 2004, the 2010 Informs Computer Society Prize, a 2013 John von Neumann Professorship at the Technical University of Munich, and in 2020 he won the Farkas Prize of the Informs Optimization Society. He's both a fellow of the American Mathematical Society and a fellow of the Society of Industrial and Applied Mathematics. In addition to more than 90 published research papers, he's co-written 2 graduate-level textbooks, Triangulations, Structures for Algorithms and Applications, and Algebraic and Geometric Ideas in the Theory of Discrete Organization. For his dedication to outstanding mentoring and teaching, he received the 2003 UC Davis Chancellor's Fellowship Award, the 2006 UC Davis Award for Diversity, the 2007 Award for Excellence in Service to Graduate Students by the UC Davis Graduate Student Association. The list is long. The 2013 Chancellor's Award for Mentoring Undergraduate Research. And in 2017, he was awarded the Mathematical Association of American Golden Section Award for Distinguished College or University Teaching of Mathematics. And in 2018, he won the UC Davis College of Letters and Science Distinguished Teaching Award. He successfully supervised 14 PhD students, 8 postdoctoral scholars, and over 50 undergraduate student research projects. Pretty amazing. So please join me in welcoming Dr. Jesus de Loera.
Thank you. Thank you very much. Let me just go back to my slides here and turn on the mic to be able to shout a little more. All right, it's a great pleasure to be here tonight. And this is a very nice opportunity to tell you about mathematics for the general public. My intention today is to, in some sense, tell you what is a mathematician, because I am sure that many of you like mathematics, and you have friends of mathematics that are maybe mathematicians, but mathematics is such an important subject in modern society, and I'm afraid that many people don't know really what mathematicians do or what they can do for you, right? So, and I'm going to use very simple examples of open questions in mathematics to show you that mathematics is alive, mathematics research is everywhere, and that we need young people to start doing mathematics to help us solve all these problems. So I'm going to talk to you about my favorite objects in mathematics. And I even brought some of my friends with me, all the way from Davis. So here are some three-dimensional models. I'm going to pass some in this side of the room so you can see, touch them. And I'm going to put some in this side of the room. Sorry, you'll get them later. So I have many pictures of these friends of mine, and I will convince you. I mean, I hope you see these are beautiful, right? They look like jewels. These are called Polyhedra or polytopes. Okay? So I'm going to talk to you for 1 hour about these beautiful objects. And many children, I often like to enjoy talking to children about these objects because children have a natural tendency to love these objects and to love mathematics. They are not shy about it. And what I tell the children is sometimes, I don't know the answer for this or that. And they're always very sure. They want to say, oh, I know the answer. I always wonder, where do we lose this energy? What happens when children stop loving mathematics? So let me show you one thing. This makes me very sad. I hope can you read this? So, unfortunately, if you Google in the internet these days, you can see all kinds of negative sentiments. But if you specifically Google about mathematics, you find a lot of very depressing sentiments of young people about, what is math good for? It's useless, right? Look at this last comment here. A meme, right? We're talking about memes these days. I'm still waiting for the day I will actually use some equations in real life. Well, my intention tonight is to try to show you that mathematics is everywhere in your life. And it's everywhere in your life because of these objects that you are holding in your hands. So that's my goal. And I hope by the end of the evening you will join me on supporting mathematics, because I do believe that we need to defend mathematics, make it more popular, make it really useful, that people realize why is it useful, okay? So let's begin by understanding a little bit these objects, because we want to study polyhedra or polytopes. You can use either one of these words. I want to study them not just in 3 dimensions. I want to study them in any dimensions, 5 dimensions, 7 dimensions, okay? So we need to understand what they are. We need to understand what they are. And to understand what they are, we can start by showing you some pictures. Of course, I brought some models. Here are some more models from my office. So I'll tell you these models were made by a priest. I'll tell you the story at the end if you are interested. And my son sent me this picture because, you see, even in nature we find polytopes. So if you look at this, this is in Ireland someplace, and you can see the shapes, the geometric shapes of polytopes appear. So we have to define this more mathematically. What are these objects that I'm trying to talk about today? Well, you can see some more here. There's a place in California, Devil's Postpile, that you can see these objects too. You can see the flat faces. You see, it's like made of flat planes, polygons glued together. You can see them here too, right? These hexagonal shapes. Okay. Here are some more. Well, not the hairy one. And so how do I construct these objects mathematically? I will say that the way what you have in your hands, these objects, the polytopes, they are like, you can think of them as what happens when I cut cheese. When I cut cheese, imagine you have a big piece of cheese. You take a knife and you cut straight with the knife. You leave some kind of flat surface, right? If you do it right, if your hand is very steady and you cut straight, you're going to see essentially these objects. You get these objects by cutting with planes, cutting with a knife, and you create a plane, and that's what you see. So in 2 dimensions, when you're studying in high school, these are just the so-called polygons, right? Is there chalk here? I forgot to ask for chalk. Oh, here's some chalk. So we are familiar with triangles, right? We are familiar with pentagons, right? And these objects is the 2-dimensional version of what you have in your hands in 3 dimensions. But if I do the same in dimension 5, 11, or 20, it's the same thing. I'm just cutting space with knives. And what I do, every time I cut with a knife, I leave this part of the cheese and throw away the other, right? So it's like I'm cutting with what I call is a half space. That's the name of this operation. So I'm cutting with half spaces, and I get this. Now, in high school, already students learn, I think in 8th grade, that you have to write an equation like 3x plus 2y less than or equal than 2. That gives you the equation of a slice, right? And the same thing happens in dimension 4 and 5, right? You get an equation like this. There is a system, it's an equation that gives you one of the half spaces, okay? Now, if I have many of these equations, I get a polytope. I get one of these objects. So what's the definition then? A polyhedron is just the set of solutions of a system of linear inequalities, okay? That's the mathematical definition. If you didn't understand, you must have seen this in high school at some point, but if you haven't seen it, it's okay. The rest of my talk will be more intuitive. I just wanted to tell you what is the mathematical way I think about it. Now, I will talk about open questions that nobody knows the answer. I'm going to talk to you about things that nobody knows how to solve in this planet, okay? Why am I doing this? Because I want to convince you that mathematics is alive, that we need so much to discover, that we still need to do so much more to develop mathematics. So these questions, I hope you will understand them. They're, I think, very simple to explain, but even the best mathematicians don't know the answer, okay? So let's talk about, now, can I have one of the models, just one of them? Maybe one of the small ones. Oh, thank you. Oh, yeah, sorry. Yes, thank you so much. Everybody's bringing me. Just need one, thank you. Oh, okay, since we have, okay, this is a big one, okay. So let's look at this model. So this model is made of many, many shapes, right? It has pentagons, has hexagons, and they're glued together. So these are the faces of the polyhedron. This is the anatomy. So imagine I'm teaching you anatomy. These are the parts of the body of this object, right? The pentagons, the many different pentagons you see, the hexagons you see, these are faces, okay? And I'm interested on how many faces can there be. So you can think about it the following way. I will have the faces that are the two-dimensional faces, but also the edges, these ridges that you see here, these are also faces. And also the corners are faces too. So the faces is very important, and I would like to count how many are there. How many possible faces can there be? Okay, so here are some examples of faces depending on the type of polytope you have. And I also brought another one. It's a foldable polytope. A polyhedron here is, you guys recognize this one? It's a cube, right? It's a famous cube. And so a face is anything that I get when I take my object and I touch a plane with it. That's a face, okay? And I want to count faces. So I make a way. So this is a very old subject. In the 1700s, the famous Swiss mathematician Leonhard Euler discovered that there are some beautiful relationships on the different types of faces. So the corners I call vertices. These are zero-dimensional faces. This is just one point. These edges here, these ridges that you see, these are one-dimensional. So therefore, I count them differently. And then finally, these hexagons, the pentagons, they are two-dimensional. So I'm going to count two-dimensional faces, one-dimensional faces, zero-dimensional faces. Let's do it. No, this is too big, maybe. Let's do it with a cube. Let's do it with a cube. So let's see. How many corners are there in a cube? Let's see. 8 corners. So that means that there's 8 zero-dimensional faces. How many edges? Well, this is very useful because there's 12, right? There's 4 on top, 4 on the bottom, and 4 around. So there's 12. Finally, how many squares do you see? There's 6. Okay, this is amazing because this gentleman, Euler, discovered back in the 1700s that if you do the same for every polytope, for example, here there's, I don't know how many pentagons, I don't know how many vertices there are and edges, but if you do the count of all the zero-dimensional faces, the one-dimensional faces, the two-dimensional faces, and you do the following formula, you always will get the same answer. Let me show you the formula. This is the formula. Zero-dimensional faces minus one-dimensional faces plus 2 is always equal to 2. This is a super famous formula, one of the most famous formulas in mathematics, I will argue. And you can check this is true in every polyhedron. Always true. Yes?
It always equals 2.
It always equals 2. Now, this is something that Euler discovered in 1776. Okay? So 200 years ago, more than 200 years ago. And then, okay, here are some numbers. For example, we did the cube, right? We did the cube. You can do it for a tetrahedron, for an octahedron. You can do it for many of these shapes. And surprisingly, you always get the number 2, right? That's what I was saying here before. You always get the number 2 when you do this formula. So we know a lot about these numbers. So in fact, we know everything that can happen. Okay, we have a complete answer. So in 3 dimensions, we have a complete answer. In 1906, this other mathematician, Steinitz, figured out to describe every possible combination of how many zero-dimensional faces, how many one-dimensional faces, how many three-dimensional faces can there be on a three-dimensional polytope like this one. It's enough to check these 3 equations. So these 3 equations make everything possible. So that was back in 1906. This gentleman figured this out in 1906. And it's not so difficult. I'm sure I can take any smart undergraduate here at Humboldt and I can teach them that. Why this is true. Okay? But you see, mathematics is still alive because the same question, what are the possible combinations of zero-dimensional faces, one-dimensional faces, two-dimensional faces, three-dimensional faces, when you look at polytopes of 4 dimensions, is completely open. Nobody knows the answer. Okay? And we are not even close to knowing the answer. It's fascinating. So I can explain to you the other question in 3 dimensions, but once you go to 4 dimensions or higher, there's no hope. Or there's no chance so far. Is the question clear? Is the open problem clear? So this could be a PhD thesis from somebody. This is the kind of question that we don't know the answer in mathematics, and we try to discover the truth about it. Any questions or reactions? Everybody okay so far?
Are there any partial results about it?
Yes, of course. So many people have worked on this, and there are some partial results. For example, if all the faces are triangles, you can restrict the question and say, well, what if, so in this example, all the faces, or the two-dimensional faces are pentagons or hexagons, but what if all of them are triangles? In that case, we know the answer. But other than that, it's very difficult. It's very, very difficult. And yeah, yes?
But you do have an equation like that first equation.
We have, exactly, very good, thank you very much. The first equation is still true. Well, there's a similar equation in dimension 4, very similar equation. It's also an alternating sum, plus, minus, like this one, plus, minus, plus. But you have one more dimension, so you need to have another negative. Yes, thank you, yeah. Okay, Another open question in mathematics, nobody knows the answer, and I guarantee you, you can explain this question to your kindergartner. I'm not gonna, you're laughing, but you will see in a moment. Your kindergarten students will understand this question. I'm not kidding you because I know, children in elementary school can understand the following question. So you might be thinking, well, how can you see in 4 dimensions, right? Many people ask me this question. You are a mathematician, you need to understand 4 dimensions, 5 dimensions, 11 dimensions. How do you do that? So the answer is analogy. Analogy. You try to use analogy of what you know in 2 dimensions, 3 dimensions, because you are familiar with that, and then you try to extrapolate. So, for example, if I try to understand, imagine you are 2-dimensional. So all of you are 3-dimensional, but imagine you are 2-dimensional. How would you understand something that is 3-dimensional? Well, you try to project it down into 2 dimensions because that's one way you can see the object. For example, if this is a 3-dimensional object, and I put light, I put an ray of light here. So here, there's a light bulb, sending light everywhere. I get a shadow. I get a shadow of the polytope. If you do that, you can go from 3 to 2 dimensions. For example, I had some pictures here. These are pictures. This is the cube in 2 dimensions. You see, look at it. If you have a light from the top here, and I expand it out, exactly I get this picture, right? So one trick that mathematicians will use, we look at the shadows of objects in high dimension down to 2 dimensions and 3 dimensions, because then we can see what they are. So we do that in polytopes. Yeah, so here are again the 3-dimensional Platonic solids that are familiar to you. But I'm going to show you one that is really the favorite of young children that like to do art crafts. So if you have young children, they love to paint and cut paper, etc. So when you have a polytope like this, imagine it's made of cardboard or paper. So imagine that you have scissors. Now you take the scissors, and now you start cutting along the rays. You cut. Yeah, imagine you're cutting here, and I open it. So if I do that in this case, and I open it, what do I get? So I cut, maybe I cut here, I start cutting, and I flatten it. I get this, right? Everybody agrees? By the way, it's not a unique way, right? There's many different ways to cut it and open it. You cut it and open it and flatten it. So that's one example where I can go from 3 dimensions to 2 dimensions. You see that? The same I can do if you go from 4 to 3 or from 5 to 4, right? I can cut, and open and flat. Are you with me so far? So, for example, how many different ways are there to cut and open? That's a very interesting question, and I don't know the answer, right? But can you guess what this is? That's a cube. It's exactly that. So it's one of the many ways I can cut, and open and flat, and I do that. Everybody agrees? So now I'm going to show you another one. What do you think this is? That's actually cut, open, flat of a 4-dimensional cube. So you see, when you cut, and open, this is an unfolding. The name of this is called unfolding, right? It's an unfolding. So this is an unfolding of a 4-dimensional polytope down to 3 dimensions. And this is a very beautiful picture. I like it. And you can do this for every other polytope. And this is a very famous picture. Does anybody know the artist's name? Exactly. This is used by Salvador Dali to do this representation of Jesus Christ crucifixion. And, very modernistic if you want, but this is actually mathematics. It's just one of these openings of the 4-dimensional cube. And by the way, we don't know all the ways that you can open a 4-dimensional cube. That's not something we know. Okay, but now let me go to the question that I always ask in kindergarten classes. When I go to do I go to my kindergarten class and I show them my polytopes, and then I ask them, do you think if I give you a polytope and you cut it with scissors that you can always open it flat? Can you always do that? So I tell the kindergarteners, I'm going to give you a polytope and I'm going to give you scissors. Can you always cut in such a way that when you open it flat, there's not going to be overlaps? You see that? Sometimes cut, and unfolding is not going to work. Look, there's a bat here, there's a bat thing. See, when you flatten it, it overlaps. Okay? There might be another way to cut and flatten it. So the question is, can one always find an unfolding that does not have overlappings? Is that possible? Nobody knows. Nobody knows. I have been working on this problem on and off for 20 years, and I don't know the answer, but this problem is older than me. So you can imagine how old this is. So we don't know the answer.
How many soccer balls have perished?
Yes. Yeah, no, actually, that's a very good question. Many undergraduates have worked with me to program computers to do the unfoldings.
Okay, good.
To do the unfoldings. So they do the smooshing, the smashing on computers, not on real polytopes. Okay? And we have experimented with these many, and we always find a good unfolding. Okay? But nobody knows. Maybe there's some really weird, long, big polyhedron with, 29,000 billion facets, 2-dimensional faces that is not going to be unfoldable, right? No matter how you try. This is a very famous conjecture, and I always tell my graduate students this, but I never tell them, well, I try not to tell the students this has nobody has found a solution, because who knows, maybe they get lucky, right? They actually say, I can do that. You should really try not to discourage people. So the reason I'm showing you these problems is because you can explain this to anybody, right? If you have this model, if you have papers and scissors, you can do it. And in fact, I think when we do kindergarten, we go the other way around. We give the kindergarten people, or the children, we give them paper and scissors, and we give them that. And we tell them, build a cube, right? That's what we do. And that's beautiful. And actually, you can use this for educational purposes. You can use this to teach geometry to children. You give them the paper, you tell them to build these things, and it's a very, very educational activity. Okay. Problem number 3. This problem is related to my PhD thesis. So 30 years ago, I was working in this problem, and I still don't know the answer. And I'm not the only person that has been thinking about this. So other people have thought about this. So let me show you the question. If you have a polygon, think of any polygon in the plane, just in the plane, like this polygon here. I can break it into triangles. And there's many different ways to cut into triangles. In fact, the different ways to cut into triangles is a famous number in mathematics that some of the faculty here probably know, the Catalan numbers. Catalan numbers. So this counts the number of different ways you can break a polygon into triangles. How many different ways are there to cut a polygon into triangles? Okay? Are you with me so far? You understand? If you have a polygon, you can always break it into triangles.
So what makes two triangulations different? Are you going to talk about that?
Excellent question. There's several ways to differentiate them. I normally like to differentiate them by putting, let's say, numbers on the vertices here. So then they really are labeled by the triangles are labeled by the triangle. The triangles are labeled by these numbers, and I just look at these as sets of numbers, three triples of numbers. That's one way to think about it. By this classification, what can happen is that, for example, the pentagon up to rotation has only one triangulation, but I'm counting them different. I'm counting them different. Yes, thank you. Okay, now let's go to 3 dimensions. Same question. Sorry?
Can you always, or can you ever get different numbers of triangles with a...
Excellent question. Excellent question. I love your question. So if you give me 2 pentagons, you will always get 5 triangulations. If you give me 12 guns, you will always get the same number of triangulations. So the number of triangulations that you get does not depend on the polygon itself. The shape of the polygon can be skewed, can be elongated or something. That doesn't matter. It's just the fact that it's a pentagon, the fact that it's a dodecagon, or that's all that matters. Everybody's with me? Yeah? Okay, now this is 2 dimensions is easy. We can, we know that every polygon can be partitioned into triangles, and we know exactly how many different ways are there. But if you go to 3 dimensions, now let's go to 3 dimensions. There's something very different. I forgot to say one more thing about 2 dimensions. So if I take 2 triangulations of an n-gon, the number of triangles is the same. It doesn't change. So the arrangement of the triangles will be different, but the number of triangles that you need will never change. For example, in a pentagon, I always need 3 triangles. No matter how you triangulate, you always will use 3 triangles. Why? Because that's really related to the number of diagonals that you have crossing by. Okay? That's always the case. Now, in 3 dimensions, well, you don't have triangles anymore, but you have tetrahedra, right? A tetrahedron is like this, right? It's like a pyramid, right? It's a tetrahedral pyramid. And the question is, how many tetrahedra do you need to break a polytope of 3 dimensions? Now I'm talking about the 3-dimensional object, okay? For example, let's take the cube. How many tetrahedra do I need to break the cube? Well, it depends. Let me show you. I'm going to show you one triangulation of the cube. Here's an eraser. So I'm going to show you one way to cut the cube into tetrahedra. Okay, it's one of the possible ways. So first I need to draw a cube. So here's a cube, more or less, very ugly cube. Okay, that's a cube. Now how am I going to break it into tetrahedra? I will show you one tetrahedron that is in the center of this cube. So the tetrahedron that is in the center of this cube joins this side here with this side here. And these 4 points make a tetrahedron. I hope you see it. There's a tetrahedron. And then the rest, there's the other 4 tetrahedra. So I have broken this cube into 5 tetrahedra. But I leave it to you as a challenge for tonight. You can do it with 6 tetrahedra too. Yeah? So you can do 5 or 6. For a 3-dimensional cube, you can use 5 or 6. That's it. There's no other possibility. Okay?
Every vertex of the tetrahedra
has to be a vertex of the cube. Thank you, yes. You are only allowed to use the vertices of the original objects. For example, if I'm going to use this and I want to break it into tetrahedra, I'm only allowed to use these corners that I gave you to begin with. Is the problem clear on the back? Okay, so here's another example. This is a bipyramid. And I'm showing you here 2 different ways to break the bipyramid into tetrahedra. One of the ways is like an orange. You know, an orange has wedges that go around the center of the orange, right? So here you can see I did 6 wedges of an orange, right? On the other hand here, I have two pyramids, right? And I break one pyramid here with 4 and with 4, so I can go 6 and 8. So these are 2 examples of different ways to triangulate this polyhedron that have different number of tetrahedra. Okay, you see this? And I can show you one with 7. I leave it to you as an exercise. You can find one with 7. This is one with 6. This is one with 7. Is it clear? So this is 6 and this is 8. You can do one with 7, I guarantee you. Just try it. But the question is, if somebody gives you a polytope and it tells you there is a triangulation with K1 tetrahedra and another one with K2 tetrahedra, is it true that you can find a triangulation with S tetrahedra for every S in between? That's the question. That's very simple to explain. And as I told you, when I was a graduate student in the early 90s, I worked on this for a long time. Never got anywhere. I mean, I know this has to be true. I believe it's true, but I don't know how to prove it. And computers have suffered with me for this. So, all right. Okay, so are there any questions so far? So how much time do I have? About 20 minutes, is that right? Okay. So I want to tell you that you might be saying, well, this is all very pretty, but it's useless, right? You say, I'm not going to convince my manager with this that mathematics is useful, right? And probably you will be right. It's true, these are just purely mathematical questions. But I want to show you that polytopes, polyhedra are not just pretty. They're extremely useful. So normally when I go to give this talk someplace, I fly. This time I drove. But let me tell you the following. There will be no airline in this country that could work without polytopes. Without these objects that you see here right now, they wouldn't work. Because, as I will explain to you in a moment, everything that has to do with logistics, the planning of UPS, every package you get with UPS has to do with these objects. Everything has to do with these objects with something called linear programming. So let me tell you a little bit about that. And here is one of my favorite quotes about teachers. So I got this from the internet too. So I was very sad when I read this. And I wish I knew who this math teacher is. So maybe I should read it for you, in case you cannot read it. So this is a student saying something that the teacher said. I think when people say mathematics is pointless, they're talking about things like systems of linear inequalities. Those are linear inequalities, right? Those are systems of linear inequalities. Or that most people will never use in their life. I literally asked my 8th grade math teacher when we are going to use this, and she said, "Oh, you aren't." I was very depressed when I found this, because these are systems of linear inequalities. And let me show you the simplex algorithm. So the simplex algorithm is the algorithm that computers use in industry to solve the following problem. So you have a system of linear inequalities. You want to look at the solutions of a system of inequalities. And we study this, we teach this in high school. We teach students this in high school, that you have a polygon, right? You have a polygon, and you want to find the largest value of some function. There's a function here that is a linear function, 3x plus 5y. And you want to find the largest value of this polyhedron inside this polygon. And normally the students learn that they need to move the line and find this corner. That's the last point that gives you the optimal solution. Well, we teach that in high school, but we never tell them that this is what UPS uses, right? We never tell them that. Okay, so yes, that's exactly the field of linear optimization, linear programming. And you want to maximize some linear function subject to be inside the polyhedron. It has to be a solution of the polyhedron. So, you know, there are all kinds of problems we teach students. I mean, I guess not brewery problems, I hope. But, you know, this is a typical situation. You know, you have a brewery that needs to produce 2 types of beer. There's some cost to each beer, and you want to maximize the profit, right? You maximize the profit, minimize, so maximize the profit, and you need to use some combination. This is a typical setup of a problem that you can put in linear programming. But the most popular application is actually in scheduling in an airline. For example, or UPS, you want to route the planes, you want to assign crew members to planes. All these things are linear programming problems. All these are polyhedral problems. We just never tell people that. Here's one of my favorite problems. I have worked on this a lot. This is a linear programming problem. You have factories that produce some objects. Maybe they produce milk. I don't know. Maybe you produce milk. And you have cities that demand milk. You know, maybe Arcata needs 220 gallons of milk a day or something. And then Davis produces 180 gallons of milk a day. And there's a price, right? There's a price from sending from Davis to Arcata the milk for a gallon. And you want to make the assignment that minimizes the cost. I mean, that's a very applicable situation. We do this all the time. You can think of this as, in many situations, you maybe have jobs, people, and jobs that need to be done. You need to assign jobs to people, right? That's another example. Hewlett-Packard, for example, has this type of problem because they have 10,000 employees. They need to make assignments of this type, right? How do you do that? So anyway, so this is the applications that you have in mind. How do the computer find the solution? In 1947, this gentleman here is George Danzig. George Danzig came to speak in these lectures. So just
I think he was about the 7th or 8th Kieval speaker, Danzig.
Yeah, George Danzig is the inventor of this method to find the optimal solutions. So the method is actually very easy to explain. You know, I teach this to undergraduates in 5 weeks because I have to teach them how to do it in the computer, but I will give you a discount. I'm going to teach it to you in 2 minutes. So it's very easy. So the method is as follows. You know that the optimal solution has to be one of these corners, has to be one of the corners of this polyhedron. So you start at a corner, say at this corner, and you know that you're going this way because that's the optimal, the linear function you're following. So you're going up. So imagine you're going up. So you are here at the bottom. So if you can find an edge that improves, you take it. You just move up. As long as you can keep going up, you move up. And when you are at the bottom, you know, when you are at the top and you cannot move anymore, you know you're done. That's the optimal solution. That's it. That's the method. Now, of course, it takes 5 weeks to teach undergrads how to program this in a computer because you need to do the numerical calculations. There are details, obviously. It's not as simple as I explain it to you. But that's the idea. It's a beautiful geometric idea. If you don't have geometric ideas, you don't get good algorithms, right? Computers can only be as efficient as you can do them programmed. You know, you need the ideas from mathematics to make computer science efficient. Anyway, so you see, then there's a natural mathematical question. How many steps do I need? So how long can I take to go from one point to the other, right? How many steps? What's the smallest number of steps I need? Right? Nobody knows. Nobody knows. Since 1947, we have been using these. United Airlines, American Airlines, all the companies that you can think of, they use this algorithm every day, thousands of computations a day. And yet, we don't understand it. Right? We don't know, nobody knows how many steps are there. And I have worked on this problem a lot, and recently some of my graduate students have made a lot of very good programs. But essentially, we want to bound the number of steps. And how do we bound the number of steps? In computer science, we will use the size of the input here will be the number of phases that we have, the number of equations, and how many variables you're using. That's essentially the basic information you need. And the best bounds we get are horrible. See, these are some of the best bounds we have, here and here. But nobody knows the answer. These are just bounds. And the correct answer that people believe is that there's going to be some simple answer like n times d, where n is the number of facets and d is the dimension. Something very simple like that. That's what computer experiments tell you is going to happen. But we don't know in reality what's the truth. So in 1957, Michael Hirsch conjectured that the number of steps, he did millions of experiments, and he conjectured the number of steps was never more than n minus d. So finally, in 2010, this young mathematician, well, he's not so young anymore, but he's Spanish mathematician, Francisco Santos, he found a 43-dimensional example with 86 facets. So 43 dimensions, think about it for a moment, 43 dimensions. This guy can see in 43 dimensions somehow. So he figured out this 43-dimensional example and showed that n minus d is false. This is not possible. His example is n minus d plus 1. So what's the correct answer? What's the correct answer? Is there a bound for the number of steps that you need that is, for example, n times d, n cubed times d to the 7? Is that possible? We don't know. We just don't know. And that's one of the most active areas of research for my research for the last 5 years. I have published a lot of papers on this topic. My graduate students are constantly working on this. We want to try to solve it, but we haven't made any progress. It's a very interesting topic with a lot of interesting consequences in some sense. All right, I'm going to finish. I want to finish exactly at 8 o'clock. Sure. So the last thing I want to talk to you is, you might think, okay, what other applications do you have for me? Okay, well, one more application. So when you have a polytope like this and it's inside the space, inside the ambient space, I can look at coordinates. I can give it coordinates, and I would like to know points that have integer solutions inside the polyhedron. Okay? Points that have integer solutions inside the polyhedron are very interesting objects. And I will show you why. I'm sure many of you like magic squares, or maybe you like Sudoku. Maybe you do a Sudoku every night. Okay, so when you have a magic square, what's a magic square? Well, a magic square is a square, and in this case a 4x4 square that has numbers, and every row sums. So if I take the sums over every row, every column, I get the same answer. So here's an example here. The sums here, I think, is 24. If you do every row, every column, every diagonal, the sum is 24. You see? So no matter how you do it, the sum is 24. That's a magic square. Okay? So question. How many magic squares are there that are 4x4 and that have magic sum 24? Very nice, very simple question. You can ask this question to anybody that understands addition, right? So this is one of them, but I can do others, right? I can do, for example, here's a cheating one. I can do 24, 24, 24, 24. Does that work? Actually, no, it doesn't work because I'm missing some of the diagonals. But let's say, yeah, I should be able to fix this. But anyway, so you see the problem, right? You have to generate all possible 4x4 magic squares that the row sum, column sum is 24.
Don't you just fill it with sixes?
You can fill it. Is that right? Does that work? Yes, I think it works. Yes, that's right. You can fill it all with sixes. That's one solution. Thank you. So how many solutions are there? So my students and I figured out a formula of every possible magic square with magic sum n. So I want a formula that every 4 by 4 magic square with magic sum equal not just to 24, but something more special. I want the row sum, column sum equals to s, whatever s is. It doesn't matter. You understand what I'm saying? We figured out a formula for this. We have a closed formula that fits on a page. It tells you exactly how many are there. Then, a couple of years later, with another student of mine, we figured out the formulas for 5 by 5, for 6 by 6. We have all the formulas up all the way to 10 by 10. But I have never been able to figure out 11 by 11. As you grow in dimension, this becomes harder and harder. When we did the 10 by 10, we needed several hours of supercomputer computation to be able to get the numbers and to get the formula together. And the formula is so big that it's almost useless because it doesn't fit on a piece of paper, right? It's so big, such a big formula, but we can get a formula. So we have been trying to understand this problem, and you might say, why do you care, right? It might sound fun, and you might say, why are you wasting your life on this problem? I will tell you why, and I think you will see differently why you should think about fun problems like this. This table is a real table from the U.S. Census. This is a true table from the U.S. Census. I'm not going to tell you where it is from because I'm not supposed to tell you. But this is some city in the United States. And I can see by race and by income. And so I have information about gender. I have information about income. And I have information about, for example, how many white people have incomes for more than $10,000 a month or whatever, right? So I have some information of your income and your race and gender. So the federal government, you can do this. You can go to the federal government, the Census Bureau, and download these tables. You can download these tables for every city that you want, for every zip code. And the U.S. government is trying to make sure that you cannot know who people are in this table. I mean, as you can see in this example, there's exactly one person of Chinese origin, right? Of Chinese origin. Of it, you can identify this individually, more or less. If you know the zip code, there is one, you can probably find out who this person is. This is not supposed to happen. So this was given to me, to the U.S. Census Bureau, because they need to solve this problem. They need to release data for public policy reasons, but they're not supposed to let everybody know, what Walden makes, or they're not supposed to tell, I guess you see professors, we know how much we make, but in general, you're not supposed to reveal it's data privacy, right? It's an issue of data privacy. So this is what I call here limitation of information disclosure. So when you release a data like this, you try not to identify the people here. Now, one thing you can notice is that the row sums, column sums, the sums in this table are the same, right? They don't change. So one trick that the U.S. government does is they switch, they put the numbers, they give you the same margins, they give you the same row sums, column sums, because that's the statistical information you need. But they don't give you the numbers. They just give you the sums of the entries of the table. Do you understand? So you see now, do you see why this is a much more interesting problem in real life? So you would like to take a sample from a specific data distribution, right? In such a way that it's not biased. It's not going to tell you the real information. But it's significant for statistical analysis. So this is becoming very popular nowadays. If you Google or you go to the websites of people, you will hear about synthetic data. This is becoming one of the hottest topics in computer science these days because you don't want to reveal the information of people. For example, the faces of people is also very bad, right? We do face recognition, and you don't want to reveal who these people are, but you want in some sense take some kind of, release some information about them that is not them, but is close to the same properties of that person, right? So you want to manipulate the face in such a way that it still captures important physical or biological information, but is not releasing the original data, because the original data is private. Okay, so doing this is creating syntactic data, and this is the principle of creating syntactic data. You need to find another table that has the same row sums, column sums, and diagonal sums. It's exactly the same process. So that's why we care. So the student that worked with me on this project is now a professor of statistics at the Naval Academy. So they work on these things, right? Real statisticians work on these things. And all right, so it's 7:59, and I hate people that go over time. I always tell my students never go over time. It's very bad manners. So let me just conclude with a few comments. So I hope you're convinced that these beautiful objects are not just beautiful objects, but they are also very good ambassadors for mathematics, right? That they can really teach mathematics and show why mathematics is relevant. And of course, they're so beautiful they appear to children. And as I hope I convinced you, they are related to many interesting applications to make intelligent decisions. We can use mathematics to be more intelligent in how we plan and do decisions. I hope I show you that math is alive and that it's growing, that there's a lot of interesting projects for young people, that you should learn more mathematics, do mathematics, and that we really need plenty of math to discover, to steal. So math is far from death. Keep going doing math, right? So thank you very much for your time and patience.